Hello. Hello. Okay. This lecture, I'm going to discuss equivalence between worldline path integral and spacetime QFT. It's going to be a long discussion, I'm afraid, but let me begin. Equivalence between worldline path integral and spacetime QFT. Now, before I begin to show that equivalence, I need to develop some tools in order to do a long analysis. But before that, I will make some series of comments regarding a result that we derived in last lectures, which is this. So we have shown that kx minus y is same after a phase with delta x minus y. This I'm going to spend some time discussing discussing some meaning and certain relevant comments regarding this relation. Some of the comments will involve general relativity as I go on, and it's not included in prerequisites. I will make these comments for completeness, for the sake of a completeness. If you are familiar with general relativity, then you might enjoy it. You might be interested going through listening to these comments. If you are not, then you may skip it, and later on you can come back to that, and you can make notes now. And if you have any questions, then that we can discuss during the weekly meeting. So this relation, the left-hand side is the overlap x overlap y, which is given by a path integral dz d lambda over the gauge volume exponential I over h bar action worldline action, and that depends on z and lambda. Where the worldline action we found that is given by integral ds 0 to 1 lambda inverse z dot square minus 4 lambda m square, where the z dot square is given by eta mu nu dz mu ds dz nu ds. That's the left-hand side, and the right-hand side is I times vacuum expectation value of the time order product of phi hat x, phi hat y. This is the Klein-Gordon vacuum that you have studied in QFT1, and this is the Klein-Gordon field of mass m. These are the two sides. Now, the comments, let me begin with this one first. Recall in non-relativistic quantum mechanics, we had this statement that a path integral is equal to actually a Schrodinger a matrix element. Okay, so elements in Schrodinger matrix mechanics, let me put it like that, element in Schrodinger matrix mechanics, yeah, by which I simply mean that it's an expectation value of certain operators. if the path integral does not have any insertions. I will talk about insertions at a later stage, but in this path integral there are no insertions, then this matrix element is the expectation value of the time evolution operator between two states, which are given by the boundary conditions in the path integral. And so this question that you could ask is that what is that Schrodinger matrix element here, which is equal to this? The answer is that we haven't discussed this part. So this side we didn't discuss in relativistic context. And we will not discuss. Next is that you see this right hand side here in this expression. It does look like it is a matrix element, but this is not the same matrix element that I'm talking here, because this is a matrix mechanics. I mean, what I mean by that is that if your path integral is for a single particle, then this matrix mechanics is also for a single particle. But here we do have a path integral for a single particle, but on the right hand side the matrix element is calculated in a field theory, in a quantum field theory, which is not a mechanical theory. It's a quantum field theory, so which has infinite number of degrees of freedom. Here the degrees of freedom on the two sides are same. The number of degrees of freedom on this side will be same as the number of degrees of freedom on the right hand side. But that is not the case here. Number of degrees of freedom is infinite here. So this is not, so the right hand side is a matrix element, but calculated in a field theory. Okay. Now, next point is that in this case, in the non-relativistic case, we had an equality, just like in here we are talking about an equality. However, that equality we did not show as in the result of two computations. Rather, we actually derived the left hand side from the right hand side. We started out with the matrix element, and then using the usual time evolution of a Schrodinger theory, we arrived at the path integral, and we showed that for certain standard systems, the Feynman path integral is an exact statement. For some others is more generic system, we can come up with we can derive the corresponding path integral statement. So this derivation is not that we do a completely different looking calculations and show the results are same, but it is actually by construction they are same. That is what is being showed here. So here, on the other hand, we are showing that certain quantity calculated in this theory and in this theory are at the end of the calculations, we see that they two are matching. But that is, I mean, if we do not calculate it, and if we do not have the ingenuity to show that these two results are actually same, we wouldn't know that these and these are same. So the question is that could we derive it from here, from the field theory expression? Just start from the field theory expression, just like in non-relativistic quantum mechanics, you derive it, and then the equality is shown at the level of construction, which we don't have to actually calculate the result and then show their equality. So that is a deeper understanding. So that is the question that we could ask here. So what about deriving worldline path integral from QFT matrix element? Now, when you start thinking about this problem, you first realize that the reparameterization invariance that we had here in this case is a gauge symmetry. Gauge symmetry in the sense of some local symmetry, which basically is introduced, which basically introduces redundancies in the mathematical analysis for a good reason. You introduce certain redundancies. That means certain additional variables which are which you do not necessarily need, all of which you do not necessarily need to calculate a physical quantity. So physical quantities are the ones which are gauge invariant, which will be invariant under this transformation. Now, so when you compare two theories, on one hand, it has a local symmetry, gauge symmetries. On the other hand, there is no natural way that it has. It's a completely different description. Then only the gauge invariant or physical quantities are supposed to be able to, you should be able to match. So there is no natural way. So only gauge or reparameterization invariant result can be expected to arise in QFT. It is not guaranteed that you will see the gauge symmetry on this side. So only gauge, or in this case, which is reparameterization, invariant result can be expected to arise in QFT calculation. And it is indeed true that in QFT calculations, if the QFT calculation is done in a particular way, which is usually called Schwinger parameterization, then that produces the same result that you get in worldline theory after fixing the gauge and all, that E integral form. Let me see if I have it here. Right. So this is this E integral form that we calculated earlier in lecture 4. This E integrated form is after fixing the gauge and taking into account the gauge volume and so on. If you do that, then that form can arise in quantum field theory calculation when done in a particular way, which is usually referred to as Schwinger parameterization. So QFT calculations in Schwinger parameterization produces result in worldline form the E integrated form. Now, another interesting feature of this result is that worldline path integral. So this calculation is done in a quantum field theory, in which and also it has a time ordered product of fields. So it has certain causal properties, and you must have studied those causal properties. Hopefully we will do that also later on. In QFT1, you must have studied those causal properties. So that causal property is automatically inherited by this worldline path integral. We did not put anything explicitly here. We just made it a Lorentz invariant action. So that is another point. So worldline path integral automatically inherits causal properties of relativistic propagator. Now let us look at this aspect a little more. There are two aspects of the worldline calculation. So two aspects of worldline calculation. One is geometry. And by geometry, I mean there are actually two geometrical aspects of this calculation. One is the metric in the space-time in which the particle is moving, which is eta mu nu. If it is a relativistic particle, I mean it's a special relativistic particle, or if you consider the particle moving in a curved background, then this eta mu nu has to be replaced by the metric of that background in presence of gravity. For people who are familiar with general relativity, in presence of gravity, that gravitational interaction is given by a curved space geometry where there is a non-trivial metric, not eta mu nu. So that is, say, g mu nu, and there is also a geometric property if to lambda. I will describe it. So let us consider. I'm assuming some amount of notion, some aspects of general relativity and motion of particle in that. As I said, if you are not familiar with it, you make some notes and come back to that later when you learn general relativity. Or you can ask questions during the weekly meeting. We can discuss it further. So suppose I draw a cartoon. Say this is a curved space. This space-time. This is a space-time which is curved. I mean, it's just a cartoon, okay? And because it is a curved space, it is given by a non-trivial metric g mu nu. And then there is a particle which is moving. That is the worldline. So this is the worldline. So ST is a space which is the space-time, and worldline is a one-dimensional subspace of ST, and that is also a space, and usually it's called manifold. It's a sub-manifold in the space-time, and it turns out that this is a geodesic, as I discussed earlier. It's a geodesic in that space-time, and the fact that it should be the classical particle should move along the geodesic comes from a principle called conservation of energy momentum tensor, which is demanded by Einstein's general relativity. So that is one causal or one geometric aspect. The corresponding metric appears here in this worldline Lagrangian action. The other aspect, geometric aspect, is that, as I said, this worldline is a one-dimensional manifold or space embedded in the higher dimensional space, and we are considering reparametrization. And as a result, so when you consider a curved space, there is no preferred coordinate system. All coordinate systems are good. I mean, there is no you cannot have a bias in a flat space. In absence of gravity, there is a preferred coordinate system, which is the Cartesian system, that is not available here, and therefore you have to consider general coordinate transformation instead of only Lorentz transformation. So the tensor algebra, that the tensor calculus that is involved in this context, is a general coordinate transformation. Okay, a tensor calculus under general coordinate transformation. Similarly, on this one-dimensional space also, you have a you are considering reparametrization, which is nothing but a general coordinate transformation in one dimension, and therefore expressions involving that should involve the metric in this one-dimensional space. And it turns out that lambda, the field that we had introduced, is actually that metric. I mean, is related to that metric. So this is like worldline metric. So we have tensor calculus under general coordinate transformation of both space-time and worldline. And therefore, this worldline action is constructed out of taking into account the geometric aspects of both the space-time and the worldline. So it's a geometric construction. The other aspect of this calculation is the gauge procedure. Which basically involves dividing by the volume of the gauge orbits and so on. Those are subtle procedures. They are all constructed, they are all developed logically, but finally when the answer matches, this gives you confidence on those formal arguments. So this gives, so matching gives confidence in those formal arguments. Okay. Now I was discussing causal properties inherited by the worldline path integral here, and then I said I should point out let me focus on this point, and then I started saying such things like geometry and gauge procedure. That's fine, but geometry, why geometry? Why geometry must be related to this? Why geometry is related to this causal behavior? Is there any? Should there be any relation? Now, it's not a very straightforward question. It is accepted. It is because we do have this direct result, and but why this result could have been expected a priori, that question is not usually explored in detail. We know that it is true, so let's move on. That's usually the attitude. But let us try to address this. I will not be able to give you a full answer, but I could tell you what I think the subtleties that could be relevant here. So the question is that why is geometry related to, or why should geometry demand causality? What's going on? Now, what I'm going to say now is that this geometry is actually a universal feature in a certain sense. Let me explain. So this is universal in the following sense. Let's consider, so as I said in some discussion earlier, that the fact that the classical particle should move along geodesic, which is not only a theoretical claim. I have discussed that in relation to Newton's laws and all, and they are observational facts. So it is an observational fact that this picture, it's an observational fact. And so let us see in nature how this is usually realized. You don't have when you observe a classical particle and formulate your theories to describe that, you never have observe a classical particle that is a fundamental excitation or a fundamental particle, right? That is always a composite object. It is not like fundamental particles described by quantum field theories and all. So let us consider a piece of stone. There are lots of ambiguity in this statement. We don't specify the material that it is made up of. We don't specify shape, size, and so on. It's a piece of stone. Is a very generic object to consider, and all we know is that there is a large number of quantum mechanical degrees of freedom which are interacting with each other to construct that piece of stone. So large number of interacting degrees of freedom, large number of quantum mechanically interacting degrees of freedom. And these quantum mechanical interactions, these are all fundamental interactions in nature. Which are all causal theories at a fundamental level. And but there are very large number of such mathematically, if you want to describe it, there are a very large number of models that you must have, because it can differ in materials, it can differ in size, shape, which means you have a varied types of molecular, atomic, and nuclear structures, and these are all confined in this piece of stone by the fundamental interactions. Now if you go to the long distance behavior of this stone, say long distance behavior, and that's where you see that it is moving along a geodesic. This is a geodesic, which is a geometric thing, which is a geometric aspect, or geometric description of something. Geodesic appears in a geometry. But then what is this? When you look at it long distance, you see only one degree of freedom, one particle-like degree of freedom for which you are constructing classical mechanics, mechanical theory, right? But actually the full theory, full description is given by this quantum mechanical system, which can be, which is, when according to the current understanding, is a quantum field theoretic system, and which describes with the dynamics of this stone. So what is this degree of freedom, this classical single particle degree of freedom that we observe? It must be on some average of all this large number of quantum mechanical degrees of freedom and their interactions. It must be some average of all these degrees of freedom. So in some sense, it is some center of mass kind of thing. I mean, there is no definition of center of mass here, but the center of mass has a similar idea. So it's a preferred degree of freedom which represents the entire composite object in a very crude and approximate manner. It's an average. It shows the average property. So some average degree of freedom, like center of mass. Okay, that's what it is. And now we know that this is how it goes. Newton's law is formulated from the observations that we make, and this is our observation. We haven't derived it from these fundamental interactions, but it is true that these fundamental interactions must be producing this result as a result of making some averaging of procedure. It must be an effective description from the same quantum mechanical theory. You pick one very complicated way, one average degree of freedom defined in a very complicated way. We don't know a priori what that is, such that an effective description for that particular degree of freedom will give you geodesic. That is what must be happening, right? And so this is like this is what I said. Long distance behavior, or one must say that it is an effective description, right? I mean, you are throwing away a large amount of information and only keeping some effective observation or effective information of the dynamics which is relevant for this type of observation, right? And the reason this is universal is that it is irrespective of what kind of matter you take, what is the size and shape, and so on. So irrespective of the microscopic details of the stone, this is going to be the observation. So irrespective of the microscopic details of the stone. So that means it must be a universal sector of all these relevant naturally occurring quantum mechanical systems, because all such systems like that form which have an excitation which is given by a compact extended composite object, all those quantum mechanical systems must be having these as an effective description of certain average degrees of freedom. So that is an universal property. So which is why which is why Newton writes down his laws, irrespective of without referring to any detailed structure, microscopic structure of the objects that it aims to describe. So this is universal sector of all relevant naturally occurring quantum mechanical systems. So from this supposedly quantum field theoretic fundamental description, which is very difficult to come up with, but suppose we have that, then from there, if you started from there, you know that this is going to be a result for certain observation. This is going to be the behavior. But if you had started from there, what you could do is to find an effective field theory from this quantum field theoretic description. You could derive an effective field theory, effective field theory at long distance, and that must be the Klein-Gordon theory. Because the degree of freedom that you are keeping, if you okay, so these are various different types of arguments from which these statements are drawn. This effective theory should be of a scalar field, and because the object that you are seeing, of course, it can have spin and all, but let us consider a specific case where it doesn't have a spin or angular momentum. So then the effective field theory must be given by, there should be a procedure which by starting from this type of fundamental theory, you take an averaging procedure and get an effective field theory of a scalar field, because the excitation that you are looking at, there are some, for example, hydrogen atom, its ground state is basically a symmetric state, right? I mean, it does not have a spin 0. So if you had an effective field theory of all hydrogen atoms sitting at the ground state, you will be describing a scalar field. So that is the Klein-Gordon field. And this is a field theoretic description. But if you, on the other hand, had a worldline description as well of these fundamental interactions, and then you will get an effective worldline theory. And that effective worldline theory will be precisely given by this one. This is the worldline path integral. But in that case, this action is the effective action of, this is a single particle of that effective averaged degree of freedom. So all the other degrees of freedom which are internal to the stone should be integrated out. In some sense, you have taken average quantum mechanical averages and come and have arrived at the effective theory of the center of mass, quote unquote center of mass, and its action should be given by this in this form, and in some form the action should be given in terms of some form where this mass has the information of these internal excitations and all. Now the form that you should get a priori you wouldn't know, but this argument shows that form, it should be possible to obtain that effective worldline theory form of the effective worldline theory by starting from the geometry, because you know that this should happen. So that is the construction. We came from here to derive this our worldline path integral, which is the effective worldline theory, or that is coming from all the interactions involving all the degrees of freedom. And these two descriptions are equivalent. This is what the result is showing. Therefore, we did not come from here. If you had come from here, then this causal behavior of this result would be manifest, would be guaranteed. But we came from here. But because of this argument, this probably guarantees the causal nature of the result here. We did not come from here. We came from like this, because we know that this description is right from observation, from Newton's law and Einstein's principle of equivalence. Combining these two, we get this, and so therefore, by using the geometry as a crutch, we arrive at a result, and then we see that it has the same causal behavior with the scalar field theory, and that is very satisfactory, and that is what we have shown. That is what is being shown by this equality.